Okay, welcome back. The last class we talked about asynchronous iterative methods, and we will continue talking about that today and hopefully finish it today and begin a new topic as well. So asynchronous iterative methods are methods that are designed for solving linear and nonlinear equations written in this form x equals g of x. Okay, and the model, the mathematical model due to Baudet, is such that at time instant j, we may decide to update component I of x, depending on whether or not it is in this set capital J, right? And if it is not in this set capital J, then xi is not updated. So I will use the time instant j minus 1 directly gets mapped onto time instant j for index I. So that's the case where I is not in the set capital J at time instant j. But if xi is a component that is updated at time instant j, then the update looks like this. So this is the ith component of the function g. And we're going to use x1. But the key in asynchronous methods is that older values of x may be used to perform the update. So which older value of x1 is used? We use this function s to denote that. So s1 at time instant j. And this is the same for all of the n components. So I'll write the last one, xn, evaluated at time instant sn of j. And this is if I belongs to the set j of j. And we have some mild conditions on this model. One is that you're never reading values into the future. So that's a mild condition because it is a very reasonable condition. Another is that we eventually use newer values. In other words, we don't get stuck on using some old values. That's another reasonable assumption, so it's a mild assumption. And then the third is that we never abandon the computation of any of these components xi, which is also reasonable if our processors never completely fail. Okay? And under these conditions, we have this convergence. I'm going to just say what the convergence is in the linear case. So convergence in the linear case for any initial guess. In other words, any initial approximation x superscript 0. Okay? And we have the necessary and sufficient condition is that the spectral radius of the iteration matrix corresponding to the matrix, and I called that T last time, its absolute values, spectral radius of the absolute value of T is less than 1. Okay, so when we have synchronous iterations, we also have a convergence result that says if the spectral radius of the iteration matrix T is less than 1, then we have convergence for any initial guess. So we have this slightly more restrictive condition for the asynchronous case. Okay, and one thing I want to point out again is that this is for any initial guess. It is possible that the spectral radius is greater than 1, of this is greater than 1, but we still get convergence. Okay? but we can't get convergence for every possible initial guess. So that's a question that we'll explore, I think, in today's exercise. Okay. Something that I do not like about this model that I want to point out right now is that when we're updating component I at the jth time step, we're using values of these, we are using these previous values, but the previous values don't have to be the latest ones, even for component I. So let's say component I is equal to 1. Okay, so I is equal to 1. And if there's a processor that is responsible for updating this, it is reasonable to assume that it also has the value 0. Well, actually, let's say not. Let's say I is equal to 1, and j is equal to 10. Okay, so when the processor responsible for updating x1 at time instant 10, it is reasonable to assume that it also has the value of x1 at time instant 9, right? Because it's the local processor. It should have all of this data. But this implies that if some other processor at this time instant is going to, let's say I is equal to 5, right? If some other processor is going to use some older value of s, some older delay, so some older value of x1, then the local processor also has to use that local value of x1. So that's slightly unrealistic. And I'll show you an example of that in a moment as well. But it's just wanted to mention that here since I have that equation up on the board. Okay. Let me show you an example. So let's say we have a simple finite difference matrix. And we talked about finite difference matrices in the first part of this course 1.5 years ago. So if you don't, was anyone here 1.5 years ago? Did anyone see me 1.5 years ago? So all of you are newer than that. Okay, so most of you have hopefully seen me on these videos. Is that right? Or I've only been told this. Have most of you seen these videos? Yes, you've all seen these videos? Okay, so you may hopefully remember these finite difference matrices. I'm just going to choose a simple, very small one-dimensional case. Okay, so here is one matrix. Okay, and for the Jacobi method, what is T? T is equal to I minus D inverse times A, where D is the diagonal of A. So T is equal to this matrix 1/2, 1/2, 1/2 on the corners. Sorry, not right. One-half on the edges, corresponding to the minus 1s, and 0s everywhere else. Okay? And if you look at the spectral radius of this matrix, it's less than 1. We know that for finite difference matrices, the Jacobi method converges. We know that its spectral radius is less than 1, right? And we want, for the asynchronous method, the absolute value of t, and it happens that for this matrix, the absolute value of t is equal to t, right? And you will actually see this is true for any finite, well, not for any, but any finite difference discretization of Poisson's equation using standard differences, which is natural actually. Okay, and so in all of these cases, t is equal to absolute value of t. So the asynchronous iteration will converge as well. So this example is mainly to say that it's not rare for the asynchronous iteration to also converge exactly in the same cases as the synchronous iteration because, in the synchronous iteration, because the matrix T already has values that are all non-negative. Okay? Any questions? All right. So this convergence is an asymptotic result. It means that if you take enough steps, you will ultimately converge, right? And now I'd like to say something about how fast is the convergence. But we cannot say anything right now about how fast is the convergence because we haven't said anything about what is the size of these delays. If the size of the delays is very large, then convergence will be very slow. And if the size of the delays is not very large, then convergence could be fast, right? So in order to say something about the convergence rate, we have to say something about the size of these delays. And I'm going to talk about the convergence rate only for the linear case. That's a convergence rate for linear iterations. So we need to say something about the length of the delays. Okay, so let's define this positive integer r as a bound on the delay. A bound on all of the delays. So meaning for any sk evaluated at the jth time instant, or any sk at this time instant, this is going to be greater than or equal to j minus r. Okay. So j is the current time instant, and r is a bound on how far back we can look, right? And how far back we can look has to be greater than j minus r. In fact, this is the condition. This is a condition that is used in the 1969 paper by Hazan and Mirenker, used by Hazan and Mirenker. And the Baudet paper just generalizes this a little bit so that you don't need this bound on the delay, but it's useful to have a bound on the delay in order to say something about the length of the delays. Okay, so that's positive integer r, and then we also need to say something about how often elements are updated. If elements are updated very rarely, then convergence could also be very slow, right? So let this quantity t be the length of the span of the time instance, span of time instance, where all rows are updated. And this means that This means that if we look at time instant j plus 1, okay, and j is the set of all of the indices I that are updated at that time instant, right? And then we look at time instant j plus 2, and this is the union of those two indices, sets of indices, all the way up to j of time instant j plus t. So these are t time instants. If this set of time instants, during these time instants from j plus 1 to j plus t, all of the indices are updated. We have n indices, and all of them are updated. Okay, this is how t is defined. Okay, and it would be like the smallest t in which this happens for all possible j, little j. Okay, so a small value of t means that elements are updated frequently, right? And a very large element of t means you have to take a lot of time instants, a lot of these instances before all of the elements are updated, right? So small t would imply faster convergence. Okay, so if we define r and t this way, then what can we say about the convergence rate of the asynchronous iterations compared to the synchronous iterations? They will be slowed down. How much slower will it be? Asynchronous convergence compared to synchronous convergence is slowed down by a factor of r plus t. Okay, so it's reasonable to be able to add these things together because both of these things are a count of the number of time instants. Okay, so to make this really clear, in a synchronous method, in a synchronous method, to reduce the error norm, by a factor of 10, okay, how many steps do we need? Asymptotically, the number of steps we need depends on the spectral radius of the iteration matrix. So we need 1 over minus log in base 10 of the spectral radius of A. Okay, we need that many steps. As an example, if the spectral radius of A is equal to 0.9, okay, in other words, we're reducing the norm of the error by a factor of 0.9 at every step, okay, then you can just plug it into this formula. Then 22 steps are needed. Okay, and then for synchronous methods, for asynchronous methods, we need r plus t divided by minus log in base 10 of the spectral radius of A. Okay. All right, so now, let me now try to give you a demonstration of asynchronous methods, but using MATLAB. So one thing that we could do is to try to implement this in parallel and try to demonstrate a real asynchronous method. But I think it's premature to do that because I think we still have to try to understand some details of the model. Okay, so what I did was I wrote a simple MATLAB program, which I'll show you on the board. So can I get the screen working, please? All right, here we go. Thanks. And is there a pointer handy? Wait, I think I have something that might work. Okay, so here's this function written in MATLAB that will simulate an asynchronous iteration for solving a system of equations. The matrix is A, the right-hand side vector is B. Okay, and I'm calling it Hazan and Mirinker because it doesn't implement the general Bade model. It implements the model that has a bounded delay. Okay, so one of the parameters to this function is this delay bound, which is the number of time instants that you can look backwards. And you can't look any farther back than that, right? So that's what the bounded delay means. And I'm going to take a number of time instances. The number will be max time, okay? And then I also need to say something about capital J, right? The set of indices that will be updated at time instant J. But instead of specifying what J is, what I'm going to do is I'm going to specify an update probability. So meaning at every time instant, there's some probability that a given row will be updated. Okay, given x value, component of x will be updated. Right, and that will be the same for all of the equations. Actually, it could be interesting to change that and make it different for different equations. And then the output is going to be a history of the residual across all of these time instances that we simulate. Okay. So how would I implement something like this? In order to be able to look back in time, a number of steps equal to the delay bound, I need to store the values of x that are computed in some kind of buffer. And instead of storing the entire history, I only need to store the previous R of them, where R is the delay bound, right? So I need storage of at least the delay bound times the number of rows. The number of rows because we need one value for each row. Okay? So I think I've explained all of the input parameters, and you can, try it on a few matrices. So let me show you how this works. And this is for the asynchronous Jacobi method, right? So in Jacobi's method, we need the diagonal of the matrix A. So here's the diagonal, and here's the inverse of that diagonal. And I'm going to start the iterations with 0 as my approximate solution. Okay? So now this is the loop that will go from one time instant to the next time instant. Okay? And what I'm doing over here is I'm going to select for each component I, which value will be used at that time instant. Okay? So this just chooses a random number between 1 and the delay bound, and it will say the values of x that are red, so x red is a vector of length n, the values of x that are red are going to be selected from the previous values that we have stored in this array called values. Okay, and that's the circular buffer. Okay? And the residual, based on the values we have read, is computed this way. The residual of the system AX equals to B. Okay? So now we're going to loop through all of the components. And for each component, we're going to decide whether or not it's in capital J for that time instant. And that's going to be based on this update probability. Okay? And then this is the most important line in the entire code, which actually performs the update. Okay? And to know how to write this line of code, we can just look at the formula for the 3x3 example that I wrote at the beginning of last class. Right? And this is the formula for it. So to get x1, we're going to compute it by using this formula where x2 is some previously computed value of x2 and x3 is some previously computed value of x3, which are the values that we selected in xread. Right? So I've just implemented that exactly over here. And I want to point out that doing something like this is wrong. Okay, so what is the difference between this line and this line? Here, I'm saying that I'm going to use the current value of xi to update my new value of xi. Right? And this is what I just said a moment ago over here. This is a reasonable thing to do, right? I'm the processor responsible for updating component I. So I should know the previous value of I. I don't have to look way back in history because nobody needed to send that piece of data to me. I already had it, right? So if I use this latest value of I, then this is actually wrong. Right? Because this is not consistent with the model. And in fact, I tried this. And what happens is that you can lose convergence, meaning that you think you have a problem in which the spectral radius of the absolute value of the iteration matrix is less than 1, but it does not converge in that case. Okay? The second line is just a simplification of the first line. And you can see here explicitly xi is used rather than the old value of xi, which is used by everyone else. Okay? So after everyone has updated, then we're going to store those updates that were just computed into the circular buffer. Okay? And then we're going to calculate a new value for the residual history. All right? So let's see if this will work. And let's try it on a one-dimensional Laplacian. So I'm going to generate the one-dimensional Laplacian using this little piece of code that I have and a corresponding right-hand side. Okay. And you can I don't know if you have, I don't remember if I gave you this Laplacian 1 code, but it's just generating a simple tridiagonal matrix. 3x3 version I just wrote on the board. Okay, and then let's compute the residual, whoops. over here, let's compute the residual history using this Hazan and Numerical function. So A, B, what should the update probability be? Let's actually choose the simplest case. Let's just say that everyone updates and you use the latest information. So that would correspond to just the Jacobi method, right? Just the Jacobi, synchronous Jacobi method. So that's the update probability. The delay bound is 1 because everybody will only store one previous value, and that will be the latest value. And the maximum number of iterations, let's say 1,000. Okay. And then let's plot the residual history. And there it is. Okay, maybe we should do more iterations because that did not reduce the error by very much. Okay, so 10,000 iterations. Okay, so there we go. So as we go to 10,000 iterations, the error norm decreases, and you can see it's starting to look like a straight line over here. This is called linear convergence because we're reducing by a factor every time, and it's going to be related directly to the spectral radius because it looks like it's an asymptote. Okay, so that is what you might think of as the best possible convergence because it's the synchronous method. Okay, so now let's keep that on the screen. All right, so now we can say, all right, what should the update probability be? Let's say 0.5. Okay, so the first one is update probability. So which means that there's a 50% chance that a element will be updated at a given time instant. And how about how many values will be used? For simplicity, let's again choose 1, okay, meaning that you always use the latest available data. All right, so this is a case that is not too complicated. And let's plot that residual history. Okay, so that's the red line. Okay, so you can see that the convergence is slower because not everyone is updating. And it's also not smooth. You can see that there are quite a few bumps, so convergence is also not monotonic. All right? But at least it's converging as we would expect because this problem has spectral radius of t, spectral radius of absolute value of t is less than 1. Right? So we do expect convergence, and indeed we're seeing convergence. All right, so now let's look at more complicated case, and we will now say now we'll set a delay bound that's greater than 1. What should we use? Depends on how brave you are. Let's use 3. Okay. And we'll plot that. Okay, so 3. So now the method is asynchronous, right? We're looking at older values of x. We're still converging. Convergence is a little bit slower. And if you like, you could try to say, well, how much slower? It's by a factor of r plus t, and you can see whether or not it might agree with theory, whether these numerical results agree with theory. All right, so now let's be a little bit braver, and instead of 3, let's say we'll use a delay bound of 30, which is really looking pretty far back in some of these cases. Okay, so do we still get convergence? Yes, we do, but convergence is eventually pretty slow. So it seems like in all these cases, convergence is pretty fast, and then it slows down. Okay? All right, so I think for fun, what we can do is do this thing, which is wrong. So instead of doing that, we're going to do this, which I feel is more natural. And in fact, when I first wrote this code, I wrote it this way because I felt that, you know, xi should be able to update using its most recent value of xi. All right, so let's do that. And let's not be so brave. Let's do this. And let's plot the residual norm history. Let's show the graph first. Uh-oh. Here we go. Okay, so you see something that is not so good. I don't even know if it is converging. Let's do something like this. Change the 0.5 to a 0.9. So should the result be better or not? We're updating more frequently. And then semilog y. Okay, so that was really bad. You can see that it just diverges, right? And that is that's really bad. So it's like the obvious thing that you would like to do is actually not the right thing to do. Which means that this model might be somewhat deficient because it's not as realistic as we would like. It's a good model because it is actually quite general. It covers a lot of cases, but actually not this case. It's also a good model because we can prove convergence for that case, whereas in this more realistic situation, what can we say about convergence? So that, I think, is a very interesting research problem, worthy of a very nice paper, if you can say something about convergence about this more realistic situation. Okay? So any questions about this so far? So what I have done, if you go onto the course website, you can see that this code is provided to you. And I'll give you an exercise to try. I can give it to you now, or I can give it to you later. Why don't I give it to you now, since you're thinking about it. No, you know what? I'm going to give it to you later because I want to show you some other things on the computer as well. Okay, so so this code is provided, and you can try it out. The thing that I wanted to show you now are some comparisons with the Jacobi method. So some more numerical experiments using MATLAB, but using a very simple, but using a simplification, which is that the delay is always equal to 1, which I think could be reasonable because it means that you're always accessing the latest available information. Okay, so we don't have this issue of non-convergence in that case because we're always using the latest available data. Okay, and in that case, it's also relatively easy to compare to the synchronous Jacobi algorithm. Okay, so let me show you some of these results. Okay, so what I'm going to do is I'm going to use a Jacobi splitting, so the Jacobi method that we've been talking about. And I have a matrix that is 100 equations, and that's just the finite difference Laplacian on a 10 by 10 grid. Okay, and I'm going to assume that I have 10 processors. So actually now for the first time, each processor is going to have more than one equation. So each processor is going to have 10 equations. And I'm going to make the assumption that each processor updates its 10 equations before the update is made available for the other processors to see. Okay? And to make this interesting, I'm going to say that 9 processors are normal processors, and they're going to update their 10 equations in 10 units of time. Okay? And then 1 processor is going to update its 10 equations in s units of time, where s is different from 10. So for instance, s could be 20, meaning that this processor is twice as slow. So there could be something wrong with this processor. It could be very busy doing other things. Okay? And I want to know how synchronous and asynchronous iterations compare when I have this case. So this could be, a load imbalance, any kind of hardware irregularity with one of the processors. Okay? So here is a plot of the residual norm plotted against the number of relaxations, or the number of updates. Okay? And the blue line is for the synchronous case where all of the processors are using 10 units of time. The synchronous case and the asynchronous case are exactly the same in this situation. Okay? And then the red curve is the curve where one processor takes 20 units of time to compute to update one of its equations. And you can see that to get the same residual norm, it's actually slower, meaning you require more relaxations. It's slower than this blue curve, but that's not exactly a fair comparison, because the blue curve assumes that there are no delays, and here we do have delays. So it's not really saying that asynchronous iterations are worse. Right? Asynchronous iterations will have to be worse if some of the processors are slower. Okay? And then for the case in s is equal to 50, one processor takes 5 times longer than the others. You can see that it's not 5 times slower, but at least significantly slower. So from this point of view, when we have some delays, even if we're using an asynchronous method, the method will be slower than if there are no delays. Okay? But the real thing that we should plot on the x-axis is time, right? Not the number of iterations. And if we plot time on the x-axis, then we have a plot that looks like this. Okay? So 10, this blue curve again, is everything takes 10 units of time per step. Right? So synchronous and asynchronous are the same. No delays. Right? And then, let's say 20, so there's one slow processor that's taking 20 units of time, but we're going to use the synchronous algorithm. Okay? So that's the yellow curve. And this means that the first 9 processors finish, the slow processor is still computing, but the first 9 processors will wait until the slow processor is finished computing before they can all move on. So that's what the synchronous algorithm means. And in this case, you can see that it just takes twice as long compared to the blue line. So over here, to get to 10 to the minus 2, we needed about 400 units of time. To get to 10 to the minus 2 with the yellow curve, we need 800 units of time. So it's exactly twice as long, which is what you would expect. But if you have 9 normal processors and 1 slow processor that takes 20 units of time per step, but you run the algorithm asynchronously, okay, then you get this red curve. And indeed, it is slower than if you do not have any kind of delays, but it is much faster than the synchronous algorithm. Okay? So from the convergence rate result that we had before, that the convergence rate is slower by a factor of r plus t, that was comparing to this blue line. So it indeed is slower, but that's not a fair comparison because you're not comparing to the case where you also have delays for the synchronous algorithm, which is this yellow line. Okay? All right, so if we have one fast processor, so we have 9 normal processors, and then one processor is actually a faster processor, you can actually see that you get faster convergence. So to reach a certain residual norm tolerance, we actually finish faster if one of the processors takes 9 units of time rather than 10 units of time. All right, so here's a plot in which I'm looking at different delays by one processor. I don't know why it's doing that. Some kind of electrical issue going on. And I plotted some of these with 100, and you can see what is actually going on, right? So over here, we're waiting for the slow processor, and as we're taking more steps, the residual norm actually gets worse. And then once the slow processor updates, then the residual norm really goes down. Okay? So there's a question in general, while we're waiting for the slow processor, is it worthwhile for the fast processors to keep computing, or should we wait? Right? And I think these results suggest that it is worthwhile for the processors to keep computing. And you can maybe see that in different ways. Here is what the maximum speed up would be for the time for different processors. So if the slowest processor is also using 10 units of time, then there is no speed up, right? The ratio of the time is 1, of the times is 1, right? But if one of them is 10 times slower, in other words, taking 100 units of time rather than 10 units of time, then you can see that the asynchronous algorithm is going to be almost 4 times faster than the synchronous algorithm. Okay? And eventually, this flattens out. And it actually is reasonable for things to flatten out because we reach a limit. After a point, if we have some processor that is really, really slow, all the other processors are continuing to compute, but they all converge on some solution based on some erroneous value that is held by the slow processor. So we basically converge, and any additional work does not give us any benefit. Okay? So this is why the curve looks this way. And this curve is problem dependent, meaning if you have a larger problem or you have different number of processors, you can get different amount of speed up. You could get very large amounts of speed up, in fact. Okay? So another way of seeing whether or not additional computations is worthwhile is to look at this question. Here I have a 64 by 64 two-dimensional Laplacian matrix, and I'm going to assume 64 processors. And here I'm going to say that each processor will explicitly perform k updates of its own equations before writing the updates to shared memory and have these values available to the other processors. Okay? So in other words, instead of having a slow processor, I'm going to say, I'm just going to update many times, and then I'm going to give my results to other people. So these are local computations that could be very fast. They don't necessarily involve communication, right? So is it worthwhile doing these additional computations? And what I'm going to do is plot something, plot the number of iterations that I need such that the residual norm is reduced by a factor of 0.05. Okay, and this is the result that I get. So if I take one local sweep between communications, then the number of iterations that I need is 100. So that's the normal case. And if I do additional work, then the number of iterations that I need goes down. Okay, and then it starts to slow down. The decrease is not as fast. But of course, these two local sweeps means that I'm doing additional computations. Okay, so it may not, eventually it may not well, at some point it may not be worthwhile to do these additional local computations. But at least initially it seems like that there is a benefit. And again, this is going to be problem dependent. Okay? And one other thing that I want to mention is this question of over-decomposition. So far we've discussed taking a problem and dividing it up into p blocks or p equations in what we've been talking about earlier, but p blocks of equations and p processors. So one processor has one block to update. But it is also very common to decompose a problem into more blocks than processors. So I have a very big matrix, I'll divide it up into many blocks, but I don't have as many processors as blocks. Okay? Which means that not all blocks are going to be updated at the same time. Right? And when blocks update, when blocks are updated, when those equations are relaxed, then the new values of x become available to other processors. So this has some kind of effect like Gauss-Seidel because the updates will tend to use fresher information. So you would expect convergence to be faster. And this is also not an unusual situation because on GPUs, graphics processing units, we always have to decompose a problem into more blocks than processors because we need to move on to other blocks. The processor needs to move on to other blocks when it is waiting for memory to arrive. Right? So while I'm waiting for memory to arrive for a certain computation, I'm going to work on another block. So this is how GPUs hide memory latency. So I'll show you an example now with 4,096 equations and 64 processors. If I divide this number of equations into 64 blocks, since the number of blocks is equal to the number of processors, the over-decomposition factor is 1. Okay, so I'm not over-decomposing. This is the case that we've been talking about before. But if we have more blocks than processors, this is an over-decomposition factor of 2. And if we have the number of blocks equal to the number of processors, that's the maximum over-decomposition we can have for this problem. We have 64. Okay, so what do the results look like here? So no over-decomposition, 100 iterations just like before. And as we decompose further, we can see that the number of iterations that we need becomes smaller. And this is because the effect of updating some equations before others has a multiplicative effect on reducing the error, and that's why we get better convergence. Okay? All right, any questions about this? I think this is the last thing I want to say about asynchronous methods for now. All right, so I will give you an assignment, and then, of course, don't go away since we have a little bit more time. I'm going to start talking about something else as well. So the assignment, I think, is very interesting. You have this code now, the Hazan-Ameringer simulation code. What would be very interesting is to try to find a matrix A and a vector B. So you're trying to solve AX equals to B. And using the Jacobi method, such that the synchronous iterations converge, but the asynchronous iterations do not converge. Okay, so the exercise is to think about how to find a problem like that and to demonstrate it using the Hazan-Ameringer MATLAB code. Okay? Let me write that on the board. So here's the exercise for next class. So it should not take very long. Try to find a problem where the synchronous method converges but the asynchronous method does not converge. That's probably too high. There you go. So how would you go about tackling this? So you want to find a problem where the iteration matrix for the Jacobi method and this matrix A that you're looking for, where the iteration matrix has spectral radius less than 1, right? That means that the synchronous method will converge, but the absolute value of that iteration matrix has spectral radius greater than 1. Okay? And the theory says that in that case, you can find some asynchronous sequence that does not converge. And I think it's a very interesting question because how easy is it to find that sequence even if that spectral radius is greater than 1? So remember, it doesn't have to, it can still maybe converge, right? But how hard is it to find something that doesn't converge? So that is the question. So you can use the Hazan-Numerical code and try different combinations of parameters. You can choose you obviously choose your own matrix, or you could even work it out by hand. Say, this is the sequence of delays that I'm going to use, and I'm going to show that it doesn't work, that it doesn't converge. Okay, so I think that a lot of ideas, interesting ideas, are in there. Okay, so let me start now on the. So any questions about that first? Let me start on the next topic, which will also involve, which you will see next class will also involve fixed point iterations and also involve asynchronous fixed point iterations. And the topic is parallel incomplete factorizations. And a year and a half ago, the videos from a year and a half ago, we talked about incomplete factorizations. And I'm going to talk about how these I'll talk about today and most of next class how these incomplete factorizations are parallelized. Okay. So to remind you, if we're given a sparse matrix A, we want to compute a sparse lower triangular L and a sparse upper triangular U such that its product is approximately equal to A. Right? And this is called an incomplete LU factorization, so sometimes often abbreviated ILU, and it is often used as a preconditioner for an iterative method such as GMRes. And one way that you can think of controlling this approximation is to say that you want to control the sparsity pattern in L and U. Okay? So L is lower triangular sparse. And we might say that L element ij in the matrix L, this is equal to 0 if the pair ij is not in some set S which we'll call the sparsity pattern. Okay, and similarly for U. So upper triangular sparse Uij is equal to 0 if ij is not in S. So S is the set of matrix locations that are allowed to be non-zero. And S always contains the diagonal elements, and that's because we always want the diagonal elements of L and U to be non-zero. If they were 0, then these factors would be singular. So S always contains the, I'm going to put diagonal in quotes because I haven't really defined it rigorously. So what is a good way of choosing S? So suppose that the set S is the set I comma j such that Aij, the ijth element of the matrix A, this is the matrix A whose factorization we're looking for, if Aij is not equal to 0. Okay, and if we choose S this way, then this is called the zero fill ILU. This is the common case. Zero fill incomplete factorization. So that's sometimes abbreviated ILU0. Or if we're going to try to compute an incomplete Cholesky factorization, in other words, L times L transpose approximately equal to A, then that's abbreviated IC0. Okay? So we want to compute an approximation with a certain sparsity pattern. Okay, there are also, as I mentioned in the previous videos, that you can choose these sparsity patterns dynamically during the factorization, but I'm not going to talk about that right now. Okay, so the question is, how do we compute this factorization in parallel? Okay, and let's try to answer that question with an example. And the example is a matrix from a small mesh, a mesh that we might use to discretize a partial differential equation. So a small 3 by 4 mesh. Okay, so I'm going to draw that mesh here. And that's 3 by 5. Make it 3 by 4. And I'm going to number the vertices of the mesh. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay? And let me now write down what the matrix looks like. And I'm just going to draw the sparsity pattern for that matrix. So the matrix has 12 rows and 12 columns. Okay? So these are the x direction connections in the mesh. And then these are the y direction connections. And we could also label the rows and the columns. 1, 2, 3, 4, 5, 6, 7, 8. Up to 12. Okay? So what we're going to do to compute the incomplete factorization is we're going to apply Gaussian elimination to this matrix, LU factorization to this matrix. But every time there's some new values that are introduced, in other words, fill in, we're going to ignore them if they fall outside of the sparsity pattern S. Okay? So what is the very first step in Gaussian elimination? So in the sequential algorithm, we're going to, in order of these columns, we're going to create non-zero, we're going to create 0 values in the first column below the diagonal, right? And then in the sequential algorithm, we're going to create zeros in the second column underneath the diagonal, and then the third, and then the fourth, and then the fifth. So it will take 12 steps in the sequential algorithm. Okay? And how about in the parallel algorithm? In the parallel algorithm, we're going to try to create zeros in the first column, right? We're going to try to create these zeros. Are there any other zeros that we can create at the same time as we're creating zeros in the first column? So can we create zeros in the second column? Because we're trying to do this with multiple processors. Can we create zeros in the second column? Can we create this zero? The answer is no, because this second column still depends on factoring the first column. Because when we factor the first column, that value will be changed. Happens to be the pivot value. And we need to know that value before we can create zeros in the second column. Right? And similarly, we can't look at 3 because 3 depends on 2, which depends on 1. We can't do 4. Can we do 5? Can we create zeros? Can we make these 2 zeros? To do that, we need to add appropriate rows of the first column. But we can't do 5 yet because the first column hasn't yet been eliminated. So in the parallel algorithm, in step 1, we can only eliminate first column. There's no other work that we can do. Okay? So things look pretty bad for the parallel algorithm. In step 2, we're going to create zeros over here. That's fine because this only depends on the first column, which already has been eliminated. But there's another column that can also be eliminated at the same time. You see which one that is? It's not 3 because 3 depends on 2, but it's 5, right? So 5, we can create zeros over here because this has already been eliminated and updating that value. So in step 2, we can eliminate 2 and 5. And similarly, step 3, we can eliminate 3, also 6, and also 9. And if you look back at the mesh for this sparse matrix, you'll see a pattern. Like we can eliminate this one, and 2 and 5 depended on 1 because they're connected. But once 1 has been eliminated, we can eliminate 2 and 5. And once 2 and 5 have been eliminated, we can eliminate 3, 6, and 9, etc. So we can eliminate in parallel the columns corresponding to each wavefront. And the number of wavefronts is going to be related to the diameter of this mesh. Okay? Which, if we have a very large mesh, we'll have a lot of wavefronts, and the wavefronts have to be processed sequentially. Okay? But within a wavefront, we do have some parallelism. So this is how you would parallelize the incomplete factorization. Okay? Once you know the sparsity pattern. All right, so what I'm going to talk about next class is an algorithm that is completely different from this, that has a lot more parallelism than what I've just shown you. Okay? So we've run out of time, and I'll see you tomorrow. I'll be here if you have any questions.